going to get started, first I'd like to say thank you to everybody who's attending this morning's distinguished lecture. I'm Jerry Lynch. I'm the Department Chair of Civil and Environmental Engineering here at the University of Michigan, and it's our privilege to be hosting the Engineering Mechanics Institute Distinguished Lecture in Objective Resiliency. Before I introduce our honored speaker, Professor Paolo Gardoni, I'm first going to introduce Dr. Amar Shakar, who's the director of the Engineering Mechanics Institute. Dr. Shakar.
Thank you, Professor Lynch. Good morning, everyone. Thank you for coming to this lecture. The Engineering Mechanics Institute is one of the 9 specialty institutes within AC. It's a small institute, only 2,500 members, but it's a very active one. We have the Journal of Engineering Mechanics. We have conferences in the US, usually at the university, and also internationally each year. And we have 16 technical committees that address different areas of engineering mechanics. And about 3 years ago, at Stanford University, Dr. Mohammed Itouni, who at the time was a principal of Wadlinger Associates, one of the top structural engineering firms in the country, right? I would say even in the world, proposed to EMI to create a committee on objective resilience. Why objective? Well, it's to distinguish it from maybe other efforts in the area of resilience, to really stress the fact that we would be focusing on models, simulation, engineering tools that allow to quantify, evaluate, and improve resistance. And that committee has been extremely active and productive. They have organized mini symposia at the 2016-17 conferences and 2018 conferences, and student competitions as well. They organized a workshop at the University of Mississippi this year in March, a short course where Professor Lynch was one of the instructors at Tongji University in Shanghai last month. And one of the committee's accomplishments was to establish this annual lecture on objective resilience. And a select committee within the whole committee has about over 50 members. The select committee has had the responsibility of selecting a speaker, someone who is very accomplished, very active and productive in the area of resilience. And that committee selected Professor Paolo Gardoni, who's going to give us today's lecture, the inaugural lecture. It's the first one. So as you see, this committee has been very active. And just I don't want to take more time because from Professor Gardoni, I just wanted to point out to you some literature that I brought about the Institute, its activities, how you can get involved, and also about our next conference, which will be at Caltech. Thank you.
Okay, thank you, Amar. Normally, the president of the Technical Committee on Objective Resiliency would introduce the distinguished speaker, but Dr. Itouni is on travel and is unable to attend this morning, so he's asked me to introduce our distinguished lecturer. So it's with a great privilege that we have the opportunity for me to introduce Dr. Gardoni. Dr. Gardoni is a professor and excellence faculty scholar in the Department of Civil and Environmental Engineering at the University of Illinois, Urbana-Champaign. He's also the director of the May Center, and I believe a lot of the work you'll see today is the work of him and his collaborators associated with the May Center. And this center is focused on multi-hazard approach to engineering. He's also the associate director of the NIST-funded Center of Excellence for Risk-Based Community Resilience Planning. Dr. Gardoni is the founder and editor-in-chief of the International Journal of Sustainable and Resilient Infrastructure that's published by Taylor and Francis. He's also a member of the board of directors of the International Civil Engineering Risk and Reliability Association, as well as the advisory council on the International Forum of Engineering Decision Making. and he also serves on a number of other national and international committees, having great impact in the field of risk and reliability analyses. He's the author of 130 referee journal papers and 7 edited volumes, and he's received over $29 million of research funding from multiple national and international funding agencies, including NSF, the Qatar National Research Funds, the National Institutes of Standard and Technology, also known as NIST, as well as the Nuclear Regulatory Commission and the United States Army Corps of Engineers. So please join me in welcoming Dr. Gardoni to the University of Michigan.
Thank you. Well, thank you, Professor Lynch and Dr. Schacher, and many thanks also to the entire Objective Resilience Committee of EMI for inviting me to deliver this lecture. The title of my presentation is Promoting Societal Well-Being by Designing Sustainable and Resilient Infrastructure. As a motivation, natural hazards can have devastating impacts on communities, and they tend to exacerbate social differences and inequalities. Probability and risk have been used as measures for decision making, where probability is typically defined as a measure of the likelihood of an event, and risk captures both the probability and the consequences of an event. FN charts, like the one here on the right, have been used for risk evaluation by comparative risk analysis, where decisions are made by comparing risk associated with different alternatives. However, looking at probability and risk alone is not sufficient. We also need to consider resilience. So today I will present a roadmap to promote societal well-being. I will introduce the concept of resilience, both as one of the most pressing characteristics of infrastructure and communities, as well as a necessary information for risk evaluation and decision making. I will introduce the concept of sustainability and its link with social justice. While I will deliberately focus on the bigger picture, I will also mention some specific engineering tools that we develop for promoting sustainable and resilient infrastructure in communities. And finally, I will introduce a broader discussion of interdisciplinary consideration that should be accounted for in addressing current societal needs, including promoting social justice. This is the outline of my presentation, and I'll start by talking about regional risk analysis. There are 3 fundamental steps in regional risk analysis. We need to model the hazards, we need to characterize the structures and infrastructure, and then we need to predict the damage. So in terms of modeling the hazards, communities might be subject to multiple hazards like flood, earthquakes, tornadoes, fire. And accurate hazard modeling then requires accounting for the temporal aspects of the hazard. For example, for seismic hazards, sequences of main shocks and aftershocks all contribute to the overall damage. For weather-related hazards, the climate change is impacting the likelihood of occurrence and magnitude of extreme events. So as to the seismic hazard specifically, which will be largely the focus of my presentation today, we develop a 2-step method to generate main shock, aftershock, ground motion sequences. First, we use the branching aftershock sequence model to generate main shock, aftershock sequences of earthquake characteristics, like location, time, and magnitude. And then for each occurrence of an aftershock, we generate synthetic time history using stochastic ground motion models calibrated using aftershock data. In addition, accurate hazard modeling also requires accounting for the spatial variability of the hazard. For example, in a region within 30 to 50 kilometers from an earthquake source, directivity effects might induce higher values of intensity measures along specific directions. The shape of the basin and the specific topography might result in amplification effects. And the characteristic of the soil and scattering phenomena might change the propagation path of the seismic waves. These factors limit the accuracy of the traditional ground motion prediction equation commonly used in seismic risk analysis. And so we develop high-resolution, 3-dimensional, physics-based models that can capture these aspects. Communities are then composed by multiple layers of structures and infrastructure. We have buildings, we have a transportation network, we have a power network, water network, just to mention a few. Each network then consists of a number of different elements. For example, in the water network, there are elements that serve the following 5 key functions: supply, transmission, treatment, pumping, and storage of water. The elements can then be divided into linear elements, like pipelines, tunnels, and canals, and point or nodal elements, like tanks, reservoirs, treatment plants, and pumping stations. For a given region of interest, we need to define the footprint of each network. The footprint of each network might exceed the footprint of the region of interest. Different networks might have different footprints, and the definition of the footprint of each network depends on 4 key factors: the type of information of interest, whether it's physical damage or loss of functionality, the existence of easily recognizable physical boundaries and the possibility to model the boundary conditions, the existence and location of strategic elements that need to be included, like generation nodes, and finally, the modeling of the damage propagation among infrastructure systems. To illustrate some of the concepts that I will present today, I will use the city of Seaside, Oregon. As part of the work of the NIST-funded Center for Risk-Based Community Resilience Planning, we consider a number of testbeds that allow us to test and verify different algorithms through calculations, experience, and intuition. One of the testbeds is Seaside, Oregon. This is a relatively small coastal community with a population that fluctuates between 6,000 and 14,000 people in season. They could be subject to earthquake scenarios originating from the Cascadia subduction zone. So for Seaside, we modeled the water network at the city level because this is a self-contained, self-sufficient system. The transportation network is modeled at the county level and then extended to the larger city of Portland. The electric power network is modeled at the state level in order to be able to run a power flow analysis. Once we define the footprint of a network, we also need to define its granularity. If we want, the resolution of the model. So we define a tributary area as the area served by a single network node. And then by changing the tributary area, we can define networks with different levels of granularity. And in the limit, the most refined model considers each single parcel or house lot as a tributary area. Then the nodal value of the quantity of interest is the spatial average over the tributary area. And in terms of modeling, different granularities affect our ability to describe the spatial variability of the impact over the area of interest, and I'll say more about this in the next slide, affect our ability to describe the changes in the network capacities and demands following a disrupting event, and affect our ability to describe the recovery process, since a skeletonized network would only include the main distribution line, but not the smaller ones. It is important to capture the spatial variability of the impact over the area of interest because certain population groups might be more impacted than others or recover more slowly, and a tributary area that are too large would underestimate the actual societal impact. So the detailed network allows us to capture the variability within the larger tributary areas used for the skeletonized networks. For example, we modeled the potable water network of Seaside with 2 different levels of granularity. One is a skeletonized model that I'm showing here on the left, where we only consider the main distribution lines. The other one is the very detailed model of the water network, where we consider each individual line going to each individual home. And finally, we can predict the damage for point or nodal elements such as buildings, bridges, distribution nodes, wind turbines. We can use fragility curves. Fragility curves are the conditional probability of attaining or exceeding a prescribed performance level for a given intensity measure at the site. For the linear elements, such as roads, pipelines, electric power distribution lines, we use repair rate curves. The repair rate curves provide the number of expected repairs per unit length of the linear element as a function of the intensity measure. So we developed physics-based fragility functions for the nodal elements. To formulate the physics-based fragility functions, we first developed probabilistic capacity and demand models based on the fundamental rules of physics and mechanics, as well as information from the field and the laboratory. This is the general expression of the probabilistic capacity and demand models, where Yk is the physical quantity of interest, X are the basic capacity and demand variables like geometry and material properties that I'm going to call state variables, and theta is a set of unknown parameters. T is a variance stabilizing transformation, and I will explain in a second why we typically need to use it. And as we move to the right-hand side of the equal side, Y hat is a deterministic model typically constructed based on the rules of physics and mechanics. Gamma then is a correction term that captures a possible bias in Y hat, which is also inspired by the rules of physics and mechanics, but is also calibrated using data from the laboratory and the field. Anything that is not captured in the first two terms goes into the model error sigma epsilon, where sigma is the standard deviation of the model error that is assumed to be independent of x, which is known as the homoscedasticity assumption, and epsilon is a random variable, which is assumed to follow the standard normal distribution. In writing this model form, I'm making three key assumptions: the additivity of the model error, the homoscedasticity assumption, and the normality assumption, which in general are not satisfied if we work directly with yk, and this is why we typically need to use a variance stabilizing transformation, so we can transform everything in the new space, and in the new space, these three assumptions are at least approximately satisfied within the range of the data. Using the probabilistic capacity and demand models, we can then obtain fragility estimates by doing a rigorous reliability analysis. In doing the reliability analysis, we need to account for the epistemic uncertainties in the model parameters theta. And we can do this in three ways. One, ignoring the uncertainties by using a point estimate of theta that could be the posterior mean, the maximum likelihood estimate of theta, simply plugged in into fragilities. To account for the uncertainty in the thetas, we can construct predictive estimates that are the expected value of the fragilities over the space of the unknown parameters theta. But in this case, we are blending all the sources of uncertainty together. To keep the epistemic uncertainty from the theta separately, we can also construct confidence bounds on the reliability index and then convert them back on bounds on the fragility. The physics-based fragility functions have 5 important advantages. First of all, the fragility functions are parametric. So once the capacity and the demand models have been calibrated, they can then be used to assess the fragility of other elements with characteristics that fall within the range of the data used for the model calibration. The modeling can be done at the structural component level, which can take advantage of the experimental data often available for the structural components, but not the full systems. The fragility estimates are obtained from a rigorous reliability analysis rather than by making simplifying assumptions on the shape of the fragility functions, like assuming a log normal cumulative distribution function. The parametric formulation allows us to easily incorporate the effects of deterioration, as I will show you later in my presentation, as well as information from non-destructive testing and structural health monitoring, which I will not show you today because of the limited time. And finally, the models account for the relevant uncertainties, including statistical uncertainty that comes from the scarcity of the data used for the model calibration, as well as the model uncertainty due to simplifications in the mathematical models. We are now using the same formulation to develop physics-based repair rate curves that are intended to replace the purely empirical repair rate curves that can be found in the literature. So far I talked about individual elements in the network. Then we need to bring in the connectivities of these elements, or if you want, the topology of the network. And this can be done using the adjacency matrix A, which is a matrix of ones and zeros, where 1 indicates that there is a direct link between two elements in the network, and a 0 indicates there is no such direct link. The adjacency matrix can be used to convert the physical damage to the individual components into its impact on the overall network. For example, considering a water network, the adjacency matrix can be used in a water flow analysis that defines the network capacity, accounting for the physical damage of the individual elements, as well as the overall network topology. Capacity of the water network here refers to the ability of the network to deliver a certain amount of water of minimum quality at the minimum pressure. Physical infrastructure often depend on each other, and such dependencies might indirectly affect a network capacity. For example, buildings need the service provided by the water and the power networks. The water network depends on the power network because it needs power at the pumping stations and control systems. So as a result, even if a network has no physical damage, there could be a loss or reduction of functionality of such network because of the physical and the corresponding loss of functionality, physical damage and the corresponding loss of functionality of a supporting network. So we need to translate the physical damage into a loss or reduction of functionality, and then propagate such loss or reduction across all dependent networks. The interdependencies among networks can be represented by using an expanded adjacency matrix. What I'm showing here is the expanded adjacency matrix for networks A and B. The top left submatrix is the adjacency matrix of network A. The bottom right submatrix is the adjacency matrix of network B, and the two off-diagonal submatrices capture the dependency of A on B and of B on A. For example, considering a water network again, the expanded adjacency matrix can be used to model the change in the capacity of the water network due to both the direct damage to the water network as well as the damage to the supporting electric power network. But not only the capacity, also the demand can be affected by dependencies. For example, building damage can lead to people dislocation that then affects the post-event water network demand. So the updated network capacity and demand can then be used in a flow-based network analysis to assess the functionality and reliability of the network. So considering the example of Seaside, we studied the effects on the water demand of people dislocation due to a seismic event. People dislocation is first estimated using a logistic model based on the probability mass function of the residential structural damage, as well as other socioeconomic factors like income and race. The fundamental idea is that individuals with a higher income are more likely to dislocate in case of structural damage. So external people dislocation then results in a decrease in the water demand at the nodes of the water network. And the assessed physical damage of the water network and the reduced demand due to people dislocation can then be used in a water flow analysis to see if the new water demand is met or not. Network components are heterogeneous, and we can have different classes of dependencies. So we develop a multi-layer heterogeneous network modeling formulation for interdependent infrastructure systems. The main conceptual shift from the current formulation is that all of the different components of the considered networks are now modeled on the same conceptual plane with different levels described with the different classes of dependencies or interdependencies. So the advantage of this formulation is that we can now include in the same model that we have different components of elements and classes of dependencies. Infrastructure also suffers from aging and deterioration over time. Aging and deterioration might considerably reduce the service life and reliability of infrastructure. They are becoming a growing problem for all types of infrastructure in the US and around the world, and they are making damage data from past events, when there was less deterioration, less informative. Infrastructure might be subject to multiple deterioration mechanisms, which could be gradual, like corrosion or alkali-silica reactions, or shocks, like damage from past events. And changes in the material and geometry, what I called before the state variables, can lead to higher vulnerability to hazards, higher fragility curves, higher repair rates, and higher probabilities of failure or reduction of functionality. There could also be interaction between different deteriorations that can accelerate the overall deterioration process. However, current formulation available in the literature typically do not take into account the possible interactions between these different deterioration processes. So we develop a state-dependent formulation to model the deterioration accounting for these interactions. The deterioration of the state variables x, or if you want, the first derivative with respect to time of x, is modeled as function of the external conditions z, as well as their own state. And then the changes in x lead to changes in the capacity of the system, as well as in the demand. And the updated capacity and demand models can then be used to estimate the time variant probability of failure. For example, considering a reinforced concrete bridge subject to corrosion and seismic excitations, the occurrence of seismic shocks accelerates the overall corrosion rate. So results show that considering the interaction of the two deterioration processes considerably affect the lateral stiffness, leading to significant changes in the fragility. There are also spatial variabilities, both in the state variables as well as in the external condition Z. So we develop an improved latent space approach for modeling non-stationary spatial temporal random fields using physics-based regressors. A spatial temporal random field V is the collection of random variables at different spatial locations S and time t, and the non-stationarity means that the properties of V vary in space and time. So the proposed formulation considers different regressors as latent dimensions and then model the mean, the standard deviation, and the correlation in the random field as function of these latent dimensions. So the proposed formulation allows us to include the influence of physical regressors with a clear physical meaning in the definition of the random field. We then couple the state-dependent formulation for deterioration that I showed you earlier with the formulation of non-stationary spatial temporal random fields to model the effects of deterioration on the state variable x, accounting for their spatial variability. All of this is done at the material scale, and then by modeling the section and element properties as function of the state variables x, we can obtain random fields at higher scales that can then be integrated in the network models. So this brings us back to the networks and the collection of networks that constitute the infrastructure in the region. So I have two quick observations. The first is because we have different infrastructure and each infrastructure is constituted of different elements, the deterioration rate can be very different, and a snapshot at time 0 can be different from a snapshot in 20 years or 40 years. The second observation is that even if we have two identical elements in the network, for example, two identical bridges, because of the spatial variability of the conditions that lead to gradual and shock deteriorations, their deterioration can be very different. So a few takeaways from this first third or so of my presentation. There are spatial variabilities in the impact of hazards on infrastructure. Some individuals might be experiencing larger impacts than others, and what I call a ground-up regional risk analysis can help predict the impact of hazards on the built environment and assess the effects of possible mitigation strategies. To look at the impact on the society, we then need to talk about social vulnerability. The characteristics of a community influence the societal impact of natural hazards. The impact of hazards on human population, in fact, are heavily influenced by pre-existing inequalities related to the vulnerability levels of the infrastructure, as well as socioeconomic characteristics of society. Vulnerable populations within communities are more likely to experience disproportionate losses and higher damage rates. So we need to couple the infrastructure impact with the socioeconomic characteristics of society to then estimate the societal impact. A number of studies have identified socioeconomic factors that shape social vulnerability. Social vulnerability is defined as the propensity of individuals to be affected by changes in the built and natural environment. What I'm giving here is an incomplete list of social vulnerability factors that one can find in the literature. However, most studies on social vulnerability are case-specific, and so they lack the quantitative generalizability that is needed to couple them with regional risk analysis. So we proposed a capability approach for assessing the societal impact of hazards. As background, Nobel Prize-winning economist Amartya Sen and philosopher Martin Nussbaum developed the concept of capability in the context of development economics and policy. The United Nations has adopted a capability approach to rank the well-being of individuals in countries around the world. There are two key ideas, functioning and capability. Functioning refers to what an individual does or becomes in his or her life that is of value. Capability refers to the specific functioning that are feasible to an individual to choose to achieve given what he or she has and what he or she can do with what he or she has. So capabilities, or if you want, the opportunities that individuals have are seen as dimensions of the individual well-being. So we propose to conceptualize and quantify the societal impact of hazards in terms of capabilities. So the impact of a hazard is captured by how it affects the genuine opportunities that individuals have. Using a capability approach in risk analysis has the following four key advantages. First of all, we are focusing directly on what matters, the individual's well-being, capturing both the negative impact as well as the possible positive impact. Using a capability approach can be linked directly and naturally with the results from regional risk analysis. A capability approach offers the conceptual resources to account for social vulnerability and also offers the conceptual resources to help in the process of risk evaluation, which is determining the acceptability and tolerability of a risk. There are 4 steps to implement a capability approach in risk assessment. First, we need to select the capabilities. Then we need to select indicators because the capabilities are not directly measurable, and so indicators are used as proxies. Then we need to develop probabilistic predictive models to predict the values of the indicators as function of the state of the infrastructure as well as the characteristics of the society. And finally, we need to develop a measure of aggregate achievement of the capabilities. So in terms of selecting the capabilities, there are 3 main considerations: significance and relevance, parsimony, and orthogonality or incommensurability. Significant and relevant means that the capabilities must be relevant to the problem of interest. Parsimony means that we need to choose the smallest subset of capabilities that include all important dimensions of well-being. And orthogonality or incommensurability means that each capability must provide information that is unique and that cannot be ascertained from any other capability. I'm providing here a list of some example capabilities that one can use along with the corresponding indicators and the indicator type, whether it's a categorical or real valued indicator. In the examples that I'm going to show you later, I will focus on the capability of being sheltered. The indicator is having access to permanent residence or being dislocated to a temporary residence, and this is a categorical indicator type. The predictive models then have the following general forms. This is for step 3 of the implementation of the capability approach. The top one is the general form for the real valued indicators, and the second one is for the categorical indicators. I will not go through the details of the expressions, I just want to point out 2 things. First, we have a consistent formulation with the probabilistic capacity and demand models that I introduced earlier. Second, the predictive models now relate the indicators I to the regressors X that describe the characteristics of the physical infrastructure as well as society. So the predictive models give the societal impact of changes to the built environment. The statistics of each indicator before a disrupting event occurs can be obtained using the measured value of each for each household of the regressors, which I call X prime here, inside the predictive model. In case of a disrupting event, then there are changes in X, going from X prime to X double prime, due to the damage to the infrastructure and the corresponding loss of functionality. The statistics of each indicator then, after the disruption occurs, can be obtained using the new value of the indicators, X double prime, inside the predictive model. For example, considering seaside, we studied the effect of an earthquake on the capability of being sheltered. First, people dislocation is estimated using a logistic model with regressors X based on the probability mass function of the residential structural damage and other socioeconomic factors like income and race. And then an indicator for the capability of being sheltered is computed from the structural damage as well as the ability of people to dislocate. And that's shown here with the blue dots on the left. So higher values of the indicator represent the ability of an individual to stay at his or her permanent residence. And this corresponds to not having significant structural damage. If there is significant structural damage, the indicator then assumes a lower value if the individual is able to dislocate to a temporary residence, and an even lower value if the individual is not able to dislocate to a temporary residence. And information on the ability of an individual to dislocate comes from the dislocation model. Reliability analysis can then be used to create an aggregate measure, which is step 4, of the overall impact on societal well-being. The well-being of each individual can be seen as a system where the indicators define the system components. So the probabilistic models developed in step 3 can be used in a system reliability formulation to define the probability that the state of well-being is above or below a desired level. So performing a reliability analysis gives us an aggregate measure of well-being based on the level of achievement of each indicator before the occurrence of a natural hazard. If a disrupting event occurs, it will have an impact on the structures and infrastructure. We can then, using the predictive model, obtain prediction of the value of the indicators of the quantity of interest, and then by doing, again, a reliability analysis, we can obtain a new aggregate measure of well-being based on the predicted level of achievement of each indicator, and this is after the natural hazards. So we can now talk about risk evaluation. We define an acceptable and a tolerable threshold to delimit 3 states of well-being. The acceptable threshold is the lower capability attainment that is allowable in principle for individual to have over any period of time. It captures demands for justice. In the word of Martin Nussbaum, a necessary condition of justice for a public political arrangement is that it delivers to citizens a certain basic level of capability. However, we recognize that in special circumstances, like in the immediate aftermath of a natural hazard, one might go below this acceptable threshold. And while not acceptable, they might still be tolerable as long as the condition is temporary and reversible, and still above an even lower threshold, which we call the tolerable threshold. The tolerable threshold is an absolute minimum level of capabilities attainment below which no individual in a society should ever fall, regardless of whether that level of capabilities attainment is temporary and reversible. And so to evaluate a risk as acceptable or not, we can look at the immediate impact. However, to determine if a risk is tolerable, we need to model the overall recovery. If the recovery is fast enough, then the risk might be tolerable. If it's not fast enough, it might not be tolerable. And so this brings up 2 fundamental questions. One is, how fast does a community or an individual recover? And this is tied to the concept of resilience, and I'll talk more about this later. The second question is, how fast is fast enough? And this is something I will not discuss in my presentation today. So a few takeaways from this second portion of this presentation. Socioeconomic characteristics of society influence the impact of hazards. The proposed capability approach can be used to gauge and predict the societal impact of hazards in a more informative and helpful way than alternative approaches. To evaluate the tolerability of the impact, we need to look at the recovery process, and in general, the more resilient are the infrastructure, the shorter is the recovery, and the more tolerable are the impacts. So I want to now talk about resilience, sustainability, and social justice. Current design approaches are pushing toward options that are resilient under different exposure conditions. Resilience means that we want to increase the robustness or the residual functionality immediately after an event, and this is tied to the fragility estimates and the repair rates that we discussed earlier. At the same time, we want to accelerate the recovery process, which is tied to the recovery curves, which I will discuss next. The actual shape of a recovery curve is influenced by different factors, including the type and level of damage, availability of resources required for the repairs, the environmental conditions, and overall preparedness. The functions with different shapes have been used to model the recovery curves, where the choice of the function has often been based on qualitative description of the situation. However, to model the recovery process in a more rigorous way, we develop a stochastic formulation that accounts for the actual work progress that needs to take place for the state variable x to recover. And we can then estimate the capacity and demand and the reliability and functionality over time, accounting for the relevant uncertainties. And we also combine the stochastic formulation for recovery with a state-dependent formulation for deterioration that I presented earlier that also works with a state variable x to perform a complete life cycle analysis using stochastic renewal theory. A common measure of resilience that can be found in the literature is related to the area under the recovery curve and is often indicated with the letter R. However, R is only a partial descriptor of the recovery curve, which is not sufficient to fully characterize it. So we proposed new resilience metrics that are analogous to the already accepted metrics in probability theory. If we call Q the cumulative resilience function, in analogy with a cumulative distribution function of a random variable, then we can define the center of resilience, in analogy with the mean of a random variable. And we can define the resilient bandwidth, in analogy with the standard deviation of a random variable. The definition of these metrics is completely general and can be systematically extended to higher order metrics, like higher order statistics, to now fully characterize the resilience associated with any recovery curve. As the individual components recover, the network functionality also recovers. For example, we look at the recovery of the water network of Seaside and a flow analysis of the network with the state variable x, the variable time, with the reduced water demand due to population dislocation, allow us to assess the availability of the water at any node over time. And we can see that immediately after an earthquake, the damaged network is unable to satisfy the minimum pressure requirement. However, after about 6 equivalent days of repair work, we have a significant improvement. The dependencies and interdependencies among networks not only shape the immediate functionality, but also the overall recovery process. What I'm showing here is the recovery process that I showed you in the previous slide that is only based on the initial population dislocation. However, if after, for example, 3 days, a household still doesn't have water, that might lead to an additional population dislocation. So considering this additional population dislocation sets us off to a different recovery process, which is typically a faster recovery process because the demand is even lower. The concept of resilience also needs to be extended from the resilience of the structure and infrastructure to describe the societal recovery. I'm giving here 2 definitions, one from the United Nations International Strategy for Disaster Reduction, and the other one adopted by the United States National Research Council. Fundamentally, community resilience is defined to depend both on the performance of the built and modified natural environment, as well as the contextual characteristics of societal, economic, and political institutions, just like the immediate impact of a hazard. So before we use the capability approach to convert the predicted impact on the infrastructure into a societal impact. This is the same figure, I just made it smaller and I put the time t0. And now we can use the capability approach to convert the predicted recovery of the infrastructure into a societal impact at a time different from 0. And so by comparing the aggregate measure of achievement of the indicators before and immediately after, we can evaluate the risk, whether it's acceptable or not. And by looking at the recovery, we can look at the tolerability or evaluate the tolerability of a risk. We implemented a capability approach using a dynamic Bayesian network, which is ideally suited for implementing a capability approach because the size of the network is not large, the network is not densely connected, and the variables are often discrete with only a few number of states. What I presented today are a number of nested models, where the lower level nested models provide input into the higher level models. All of these models have a set of parameters that generically are called theta here. They are often assessed or calibrated independently. So we develop a Bayesian updating for probabilistic multi-level models of interdependent infrastructural systems using heterogeneous field data. The methodology allows us to update the model parameters in all of the lower level nested models, considering different data types as they become available during the recovery. We can now talk about sustainability and link it with what I said earlier. There are three key aspects in sustainability: environmental justice, global justice, and intergenerational justice. According to environmental justice, a flourishing natural ecosystem might be seen as good in itself and for instrumental reasons insofar as a flourishing natural ecosystem is important for the well-being of individuals. So to incorporate a concern for the environmental justice in the proposed framework, it is necessary to consider the environment in the selected capabilities. And this can be done either in the form of an individual capability focused specifically on the environment, or with environmental regressors that capture the impact on well-being of a hazard as it changes the environment. Global justice in the immediate impact and recovery process means that there is fairness in the distribution of the impact across individuals and groups affected, and means that the resources and opportunities for recovery are available to all individuals. Intergenerational justice calls for respect and ideally promotion of intergenerational equity. The first two aspects, environmental justice and intergenerational justice, are possibly the most intuitive and definitely the most talked about, so I will not discuss them any further in my presentation. Instead, I'll say a few more words about global justice. Global justice means that we should not only look at each point in the region of interest in isolation, because there could be inequalities in the impact and the recovery rate across the population. For example, considering seaside, we can see which parts of town are likely to be most impacted by a hazard and which parts of town are more likely to recover more slowly. The example of seaside shows that certain population groups, in fact, are more likely to be impacted than others. We can see that an earthquake is more likely to affect the capability of being sheltered, as I'm showing here on the right, for individuals with a lower income. The income is shown in the center plot with the green dots, even if the physical damage is comparable. Physical damage is shown on the left. So considering an average impact over the entire city would underestimate the actual societal impact. And this speaks to the importance of properly defining the granularity of the model that I introduced earlier at the beginning of my presentation. The results also show how a hazard might exacerbate social differences and inequalities. So fairness in the distribution of the impact and recovery should be accounted for in risk evaluation. So in parallel to what I said earlier for the evaluation of risk at the individual level, one way to take into account these justice-based considerations is to define ranges of permissible inequalities. If the inequalities are likely to be exacerbated too much, either in space or time, then the risk might not be acceptable. If the exacerbation is limited, then the risk might be tolerable as long as the exacerbation is temporal. Moving forward, we also need to incorporate the role of insurance, since it can play an important role in redistributing and transferring risks and provide financial tools for recovery. We need to consider the ability of individuals to adapt and recover independently from the recovery of the built infrastructure. And we need to pay more attention on the quantification of the cost and benefits of mitigation strategies, urban planning, and public policies to find an optimal solution. So in summary, natural hazards can exacerbate social differences, but what we call a society-based design of infrastructure can promote social justice. Natural hazards can exacerbate social differences because of different exposure to hazards, different exposure to climate change, different exposure to deteriorating conditions, different social vulnerability, and different access to financial tools. Regional risk and resilience analysis can guide the development of mitigation strategies, urban planning, and public policies that promote social justice. And the proposed capability approach is ideally suited for risk and resilience analysis, for the quantification of the consequences in the immediate aftermath of a hazard, as well as during the recovery phase, for the evaluation of risks as acceptable or tolerable, and as a tool in the development of infrastructure that ultimately promotes social justice. Thank you.
So we have time for a few questions.
voice, but when you were describing social vulnerability, and you talked about some key elements being the access to clean water and shelter, I was surprised that food was not included there as part of one of the things. It maybe comes along with
That's a very good point. So one needs to select a set of capabilities. And I can probably go back if I can fish it out. But, so as a set of capabilities, access to shelter, food, transportation. So I think when we did a full analysis, we had about 6 different capabilities. And food is one of them, actually. And what I focus on here is, I just picked one of them, which is shelter. And I looked at how much that specific capability is impacted by damage to the infrastructure. But similarly, in fact, from a different source of funding, we're looking at access to food. And that is exactly looking at the capability of being, the name of the capability is being adequately nourished. And basically it's access to food, a good quality of food. And what we're looking at is how the transportation, how the natural hazards impact transportation, but also the actual buildings where supermarkets, for example, are located, where the employers of the supermarket are located, because if they have to dislocate, then the supermarket might have to close. So it's a set of elements in the built environment that are needed to have access to food, and that is a different capability. As a matter of fact, I have another presentation similar to this, which I won't pull out, don't worry. But it's similar to this, and that focuses on access to food. I just picked one here to show you more how the process is done, and one goes through the same process with different indicators for a different capability, and that's where we do the reliability analysis. Because then, as a system reliability, you need to have access to a shelter, and you need to have access to food, and you need to have access to transportation and so on. So that's where we do the reliability analysis, comes by taking all of these elements, or these capabilities, as components in a system analysis.
You may have talked about this, and I may have just not been able to quite catch it, but it seems like there's 2 distinct ideas that you can take this work in, and the one that I've gotten from your presentation is about addressing social justice issues in the recovery to a disaster, in the sense of returning to the state prior to the disaster in a way that is most equitable to the community. And of course, a lot of disasters can be used as catalysts for change, to leave a community in an equilibrium that is fundamentally different than the one before the disaster, and to use the disaster as the sort of disruptive event to achieve that. So I'm curious how your methodology extends to that, and if that's
That's a very good point. And in fact, again, I'm very tempted to go back to that slide, but I'm going to refrain, otherwise you see all this. When I introduced the concept of capabilities, when I was going through the advantages of the capability approach, one of the advantages is that we can include both the positive or the negative, most of the time the negative, but also the possible positive changes in the opportunities, because the capabilities are basically opportunities that people have. And if we look at the before and after, it doesn't necessarily mean that your opportunity will go down, or will be reduced, because maybe immediately after might be reduced, but it could be new opportunities that come from the recovery process. I mean, one of the obvious examples is after the Kobe earthquake. Kobe never really recovered as an harbor because the entire business went to Yokohama, and Yokohama has been booming since then. So for Yokohama, it was a great opportunity. And strategically, it's closer to Tokyo, it's a better location. I don't think it's ever going to go back to Kobe. So in the capability approach allows you exactly to do that, to bring in the changes that could be positive or negative in the opportunities that the people have. there remains an issue. And so I didn't say anywhere in my presentation that the resilience is to come back to the original state. As a matter of fact, that would be a mistake, because rebuilding, reconstructing really gives you the opportunity to do things differently. In the worst case, imagine this building had to collapse for whatever reason. Would you build it identically? Or you might make some tweaks and changes, right? So it really creates opportunities. Because most of the time things have grown organically in an urban environment, and a natural hazard gives you an opportunity to rebuild, and rebuild probably better, both in terms of functionality, in terms of reliability of the system, and so on. But there remains issue with, or if you want, there's yet one more reason why it's important to look at the spatial variability. Because you cannot look at, if you look at Japan as a whole entity, then Kobe earthquake was a good thing. Because really it's brought up by the benefit of Yokohama. But you have to recognize that there are spatial variability, and one might be good for some, and you don't want to ignore it, okay? But it might not be good for everybody. And so that is why the spatial variability over the region of interest is very important, because there needs to be some degree of fairness, and that's where then public policies should help in helping the parts of the region of interest that are most affected, that recover more slowly. And this is more of an engineering oriented, and I'm providing a tool for then policymakers and decision makers to make the appropriate adjustment, and which I'm not discussing here. I wouldn't be qualified to say what they are. But that's an important thing, and you cannot just look at the bigger picture. And that's why this is true, in my example, at the national level, but even a single city level or a county level. You can have parts of the city or the county that we saw it for Seaside. I mean, there are parts of the city that would be impacted more, some impacted less. And if you don't include that, you only have an average impact. And that average impact might not be too bad. But some people are really suffering much more, some people are not at all, and that gives you an average impact. But really to make the right decisions, you need to bring in the spatial variability.
If not all of them, started like T0 at the time of the event. So say you have a hurricane and you know it's approaching, can you adjust that time at which you start T=0 to be like preparedness before the event actually hits?
In terms of, that's a good point too. The T0 I have here is more, of course, is an arbitrary time that you choose, it's not a specific date, and is more on the state of the infrastructure. So if you make some changes, I don't know how much you can really, in case of an earthquake, basically nothing. Maybe in case of a hurricane, you can have some degree of preparedness, and so you can shift, if you want, your T0 at that time. If you think about, I think it was 2000, late 2000, there was an evacuation of Houston. I think Hurricane Rita was approaching. And so there would be an earlier evacuation, which is not induced by the physical damage, but because of an ordinance of the city. And so in my model, you would have a population dislocation up front before the actual damage occurs because of an ordinance. And so you can bring it in the modeling here. And if you have time and you make changes to the built environment and the actual infrastructure, which is less likely because that typically takes more time than you really have, you can include it in the state of your structure and infrastructure. You want to build a seawall and you have time to do that, that becomes the new value in your model. So the X would reflect the state of the infrastructure at that time.
Two-part question. First part is if you have been able to validate or calibrate any of the models with real-world events. And the second is I know a lot of them are predictive, so do you have plans for testing them in practical scenarios?
Yeah, very good point. So one of the challenges when you have a model of a complex system like the one we have here is that how do I calibrate it? And how do I use data from the past to make tweaks in my model? Okay. So there are three pieces in place that kind of addresses these two questions. First of all, I was stressing the physics-based and how things are from a ground up. So you can see in the literature other approaches that are much more empirical and top-down. And they look at, okay, let's look at past data, and we look at how long it takes to the power network to come back, empirically, based on historical data. But to me, that's pretty useless, because unless you're going to have the same event in the same city, your data will not transfer to a future case. And so what we have is the complete opposite. It's really a ground-up approach, where we are trying to model each individual piece and assemble it. And the nice thing is that once you have these models that you can calibrate, because they're individual pieces, you can test some in the lab, some might be from historical data from other places, but they are a smaller component, like the building blocks of a Lego. And then when you put it together, the same model can be used for Los Angeles, can be used for Miami, can be used for Houston, can be used for Seaside, which is a baby version, just because it's easier to do it. But I have the same building blocks. And so I don't develop a model that is specific to a city because I have data for that city, and then I'm not able to transfer it or transport it to a different city. Because we have the building blocks, and the building blocks are calibrated, and we have much more data at the building blocks, then I can assemble the building blocks, and I can use this model for somewhere else. So that is the fundamental idea of much of, that's the same idea that I'm, if you want, extrapolating to a regional risk analysis that we had now years ago for the fragilities. Because if you look at the literature, there are the empirical fragilities when people look at the historical damage, or maybe even some very few tests on the full structure. But then you have something that is developed for that specific structure. How about if you make a change in the design? If you have a longer span or different columns, how am I going to transfer that fragility to something like this? But if we are modeling the individual elements, then when you assemble it, it's going to be holding true also for a different system. So that's exactly the same idea here. The other aspect, toward the end, I was talking about the Bayesian updating. Because if something happens, this is going to give you the best guess up front, at the beginning, so that you can have policies, you can have mitigation strategies based on our best guess. But if something happens, now for earthquake, we don't really have a lot of data yet, but for hurricanes, I mean, almost every year in the fall, there is a hurricane season. So we can really start collecting data from that. And that can help then making, with the Bayesian updating, make all the different tweaks. And the nice thing with the Bayesian updating, the formulation that we developed, you can have data at a certain, these are, as I was saying, there are a lot of hierarchical model or nested model. We have the model for the hazard that goes into the model for the infrastructure, and then the infrastructure are assembled, and then the functionality, and the functionality goes into the impact on the society. And if you have data at any level, you can update everything below. So if we have data on the functionality of the water network, that means that we can update the models for the water flow analysis. We can update the model for the physical damage to the water network. We can update the model for the earthquake or hurricane or whatever is the hazard. So everything below can be updated. We have there is an issue of identifiability. We have many more parameters to calibrate than the data, and that's why we already have a model in place, and this is going to give us a prior for the parameters, and then they can be updated even with just one data point. The other piece of the question, we are trying to, all of this is built on a baby problem, which is Seaside, okay? Because if you implement something like this on a city like Houston or Los Angeles, well, then you kind of need to believe in your results, but it's very hard to check the things are really making sense. So that's why we started small. We're now developing something like this. Oh, by the way, maybe I should say, we have already developed something like this for the entire Shelby County, which is about 1 million people, includes Memphis, much larger. And the idea was to use a test bed where we have a sizable population. It's a much more complex network. For the power network that I didn't describe too much even for Seaside, but when we look at Shelby County, we had to model the entire state of Tennessee power network. in order to do a power flow analysis, because you need to know where the power is coming in or not. And so even though we're looking on the Shelby County, which is at the bottom left corner of Tennessee, we have to model the entire state. And so that becomes much more complex, and now we're developing a model for Houston, and the idea is we can make a prediction, and if something happens, we can check. In case of a hurricane, there will not be an earthquake. If something happened, we can see whether more of a hindcast, whether we got something right or wrong. So that's more. That would be more the ultimately verification that what we have is correct.
I have a question. First, thank you very much for an outstanding talk. And one of the things I really loved about your talk was really this notion of sort of bringing in the social element, social vulnerability, and looking at a lot of these questions. But when we think about resiliency and trying to objectify resiliency analysis, we're going to be very dependent on financial considerations. So you talk quite a bit about recovery rates and recovery curves, but they're really going to be derived based on functions of financial markets and insurance industries and things like that. What consideration do you give in your modeling there? And how uniform is the reaction of sort of the financial consideration to a disaster between the disasters we've
That's right.
seen that gives us sort of tractability of that problem?
That's a very good point. That's why in my future work, hey, we need to incorporate the role of insurance as the can play role. So largely what I showed here is the recovery. And when I talk about the stochastic formulation for the recovery, this is to incorporate the actual engineering work. But if you're not breaking ground for 1 year because of other financial and political reasons, my model is shifted by 1 year. It's basically tell you how long it would, it's more of a construction management approach, how long it would actually take for the physical work to take place to recover. But there is a lag, which could be due to the insurance time, other sources of funding. So there is a distinction that needs to be made between companies, power and water networks, and individual residents. Because the financial aspect will come in a different way. What I've showed here is largely for the water network, which will likely start immediately after or shortly after. When it comes to a company, we did some model for a hypothetical company, shipping company in Memphis. And the assumption there is that the company itself would actually be able to start relatively quickly. In Japan, for example, it's actually interesting because in Japan, most of the companies don't insure against natural hazards, but they have a line of business where they keep some money on the side in case something happens. That way they can spend this money right away and then come back right away. Housing is a different story. And again, it comes back to the difference between, which I was stressing here on income, because a household that is well off might be able to start the repairs, dig in their own savings, even if the insurance hasn't paid off yet. They might be able to find a different temporary home relatively quickly. Households that are less well off would be more vulnerable to the delays in the payment from federal help or other insurance, and so there will be a lag time there. And that brings in, so short answer here, the complexity comes really in for residential buildings. Utilities, I think, is less of an issue. Large companies, they should have enough money on their own to come back relatively quickly, at least if we think internationally. For residential homes, or for homes or residential buildings, it's a different story. And I think is again the difference that I was stressing here between high income and low income. Low income will more likely be affected in terms of the ability to be sheltered. And I was looking more at the initial impact here, but it's also likely, which I didn't have in here, that there will be a longer lag in the recovery time than families that are better off. Families that are better off are more likely to have financial ability to go to a different home, afford going to an hotel, maybe even not going to work on Monday morning, and that's still okay. So the impact will be less and will also be likely to recover more quickly. A household with a lower income, I was showing here, is generally more impacted and will also be likely recover more slowly because of the delay in the funding.
Any other questions? All right, if not, let's again thank Professor Gardoni.
Thank you.
Present him with a certificate. Thank you. On behalf of the chair of the committee.
Thank you.
Thank you again.
Thank you. Thanks a lot. Thank you.